And we'll go ahead and get a new marker because this marker is kind of fading. All right. So the first concept we want to take a look at is the idea of a probability experiment. And so I'll give you the straight definition from the book, and then I'll talk about different ways. It says here, is an action or trial through specific results. Counts, measurements, or responses. Okay. So let me give you an example of this. A probability experiment might be a roll of a die. One die. When we say dice, we mean two dice. Okay? One die is a cube with 6 numbers on it. A dice is 2 of them. Just weird. A flip of a coin. Each time you flip a coin, you have an outcome, which is the result of a trial in a probability experiment. So each time you roll a die, you get a result. That result is an outcome.
How do you spell die? Like dice thing.
Die.
Oh, just like death or?
Like die, like
die. Okay.
So the result of a trial and a probability experiment is called the outcome. So every time you repeat this experiment. You draw a card, you flip a coin, you roll a die, or in some cases, you would consider a poll probability experiment. Okay? Now, there's also the concept of something called, well, I'll wait because I'm going to run out of space. I'll do this up top. Mary, I'm going to erase here up top. Not going. So we have sample space, which are all possible outcomes of a probability experiment. That's a sample space. So before I continue, let's say your experiment is rolling a die. Okay? We're rolling a die. The sample space, which we're just gonna abbreviate with S, equals 1, 2, 3, 4, 5, 6. Do you see that? The sample space is all the possible outcomes the probability experiment has. So here's your sample space.
Mister.
Yes.
So in any case that it will be a dice, then the numbers will repeat itself again.
So if you had a dice, then the sample space might look. May I erase this, guys? Okay, I'll wait for some. I'll show you right now. They're copying this one. Okay. So I'm gonna erase this right now because they took a picture.
Yeah, it's, I mean,
You're welcome. So in the case of rolling dice, the sample space so S 1 1 1 2 1 3 1 4 1 5 1 6 2 1 2 2 2 3 2 4 2 5 2 6 3 1 3 2 3 3 3 4 3 5 3 6 4 1 4 2 4 3 4 4 4 5 4 6 5 1 5 2 5 3 5 4 4 5 5 6 6 1 6 2 6 3 6 4 6 5 6 6. There's 36 possible results.
Mr. Type of deal, what are you saying?
All right, so when you roll a dice, you get two results, right? One from the first die and one from the second die, right?
Mm-hmm.
And so you might get both dies 1 1,
Yeah.
or maybe 1 2,
Oh, okay.
all the way to 6 6. So this goes all the way to 6 6. Any questions or concerns on that? Questions or concerns on that, guys and gals and others?
Wait, instead of having to count like one by one, is there a way to like just tell like how many outcomes there are?
Yeah, it's called the counting rule, which we're going to go to very soon. It is. There is a way to tell how much results you get. It's very simple. It's called the counting rule.
So for example, like flipping a coin, it's only 2 outcomes.
Yeah, quickly, let me show you the counting rule right now. I'll ask you a few questions. How many results can you get from the first die? How many possible results are there? 6.
6.
Then how many results can you get from the second one?
Also 6.
Also 6. So it'll be 12.
6 and 6, 36. You have 36 possible results.
Oh, it's
Oh,
6 and
that's it?
6, never mind.
Okay, that's the counting.
Oh, I thought there would be more in there. Okay.
It's super simple. Okay, now, do you guys understand the sample space? What it means? Okay. Can may I erase this here or you still copy? We're good? I'll see if some of you are still copy. Go ahead. Now, guys, again, I'm basing this on the honor system. I totally understand right now. I'm not at my monitor. I can't monitor if you're on camera. It's up to you. You know, if you don't want to learn, that's fine. You know, but those of you who want to learn, I'm happy for you. I can't monitor your faces right now. I'm on the board. So it'll be the honor system, if that even means anything nowadays. It still means something, right? The honor system means something, right? I'll give it to well, next, I'll give it to them and I'll give it to this. Okay, may I continue?
Yeah.
Good. All right. So I'm gonna go ahead and erase this here. And let's talk about an event here. So an event is a space, is a subspace of the sample space. Let me use the word that the book used, a subset. Send this back.
Sorry, Mr. My internet went out. My power's been flicking on and off for a couple minutes.
Yeah. They said to just stay at the end of class, okay?
Stay on what, Mr.? Sorry?
You send me a message, stay at the end of class, okay?
All right.
All right, so let's talk about what's a subset. So let's say I got one event here. So here's the event. The event is odd numbers. So this event will be what? So the event of this space that qualifies odd number would be what? 1, 3, 5. This is a subset of the sample space. The sample space is all possible outcomes that you can have. An event is a particular subset that we're interested in. Now, one might make this might say, well, the sample space is itself a subset of itself. I'm like, yeah, maybe. You know, okay, whatever. But that's not, that's just not it. Okay, if I asked you the event of greater than 4, it'd be what? Greater than 4, it'd be 5 and 6. So we have a probability experiment. We have an outcome of the probability experiment. Now, on any particular row of a die, the outcome on the first row might be 1. Maybe in the second, it might be 1 again. Maybe you roll 6. Maybe you roll 5. Maybe you roll another 5. Maybe you roll another 1. Maybe you roll 3 or 2. You see? Those are individual outcomes that we can go ahead and record. So in theory, I can ask the class, hey guys, roll a die, I don't know, 108 times, whatever it might be. And you record each time what happened, and at the end you tally it up. And then we do it to everybody in class, and then we make a chart and see, what is the probabilities. And what happens is something interesting happens. If you flip a coin 100 times, it might not be perfectly 50 and 50. But when we flip it 1,000 times, if I have 10 groups of kids flip it 100 times and record it, it's going to be almost 50-50. It's interesting how that happens. It's very interesting. And of course, that has to do with classical probability, because not all probabilities are classical. Okay. Now, sometimes we have an experiment that is composed like a compound experiment that we do 2 things. So I'm gonna go ahead and erase this, guys. So maybe you have an experiment where you toss a coin and then roll a die. Maybe you have that experiment. So this is the experiment. First you toss a coin, then you roll a die. So let's talk about the sample space for each one of these individually. If you just toss the coin, what is my sample space for tossing a coin?
Heads and tails?
You're
1
right.
and 2.
Comma tails. If you roll a die, what's the sample space for rolling a die?
1, 2, 3, 4, 5, 6.
Now, if you do them one after the other, toss a coin, roll a die, what would be the sample space of that? Well,
1.
heads and a 1, or maybe heads and a 2, or maybe heads and a 3.
And all the way up to 6, and then tails and a 1, tails and a 2.
Cynthia, you're really late. Like,
I know,
super.
I'm sorry, mister.
Okay.
I admit I'm in the wrong.
Okay. Thank you, Mom. But what time does class start? At 7, what?
20.
Yeah, okay, well, don't make it a habit because you miss a lot of notes now.
Yes, mister. Vince, can you send me like the rest from the beginning, please? Thank you.
But
Hey, everybody's been so stand-up today about being late. They either admitted it or, that's awesome.
I was contemplating whether or not to oversleep, and I was like, you know what? Nah.
Same. I really did not want to get up.
I was
I didn't sleep.
coming late to work today, but for some reason, if I come late, I no longer can complain to you guys that particular day. I'm sorry. I get it if you mess up once, but you can mess up. There's a few ways to mess up, right? There's one willful messing up where you're like, I don't care. And there's another one you actually like you just messed up because you hit the snooze button and or you were too sleepy and you're waking up and you're like completely worried that you're late now. So that can happen too, but that happens once or twice in a decade for most people. I talked to a police officer the other day. He's like, man, I was late last week. And he's like, oh, when was the last time you were late before that? Like 10 years ago. I'm like, oh my gosh. It's kind of like that. And then everybody in the department told him, yeah, don't worry about it. We thought you had gotten into an accident. All right, so this is a sample space. Now, does everybody understand the sample space? How many results do you have there?
12,
12.
How many possible results do we have here?
2.
How many do we have here?
6. 6 times 2.
6 is?
12.
You see that? That's how you can figure out how many possible results you have quickly. All right, so now let's talk about an event. This event is heads and even. So what are these here? Event, heads and even. This guy, this guy, and this guy. Do you see that?
Yes.
Yes, sir.
Okay. Now, let me give you another event. Heads and 3. How many results are there for heads and 3?
1.
1. Whenever you have an event that there's just one result to it, we call this a simple event. We have a name for it in this book. We call it a simple event because there's one result. This is not a simple event. We don't call it a complex event, okay? We just say it's not simple. For those events that we are interested in, that there's only one possible result, we say that those are simple events. So now we go ahead and talk about the fundamental counting principle. I'll wait till some people are writing, so we'll go to that. Now remember, guys, next 9 weeks, the class is gonna be the same. I'm gonna lecture, you're gonna write notes. We'll do some problems in class, practice. You'll get some assignments. And that's it. I think I'm gonna keep on doing it through Teams. The last 2 weeks I've done it via the chats because I wanted to make sure that nobody was hurting their grades by not turning in something into Teams. Okay, so basically, if you didn't turn in during classes, you didn't feel like turning it in. You weren't doing anything. So I think I'm going to continue doing that. As far as quizzes and tests are concerned, I know of college kids who are cheating on every test they have. And I think the professors know it too, and everybody's winking at themselves because you're giving me a test online and you just, and I'm at home, I'm going to cheat. Now you guys here, if I give you the same test and I give them a test, you guys are at a disadvantage. True or not true? Now, I'm not questioning the integrity of you guys. Okay. Of any,
Mister, if someone wants to cheat, it's on them.
you're
I
right.
mean, it's bound to happen.
They're only cheating themselves.
I don't disagree with you. And you truly know yourself whenever you're gonna cheat, if you cheat or not. It's really tough, especially when you care about something. You're right, but here's the thing. I know that as individuals, I don't know that you're gonna cheat. But as a group, I know that someone's gonna cheat. And the problem is that they're at an advantage. And then when grades are competitive, and then I might as well not do that. So I don't want to add that level of complexity to the class. We're just gonna turn in stuff and that's it. That's as simple as that. I might look at your notes and say, oh, these notes are not, I might be a little bit more difficult on your notes looking at them. And of course, if the assignment, if you're scribbling everything, and I can tell that you're not putting in a lot of effort into it, then it's kind of subjective. I know, but I also did the answers, also did the notes, so I know what to expect. And I know if you're missing all that, and I can show you that you're missing all that, then I don't have to give you an A, I can give you something less. Now, some of you might say, you need to give me a rubric. I'll give you a rubric, no worries. It'll be a standardized rubric. All right.
Mister, can you move real quick so I can take a picture and copy it later?
Yeah, me too.
Thank you.
You're welcome.
Also, did you hear? Also, do you think that we're gonna go back to like most people like MOS because of the COVID case?
There was one COVID case, and then every kid that was in the class, for those kids, including the teachers, were asked to stay at home, and as a precautionary measure, and so they're monitoring everybody. The teacher next door was it. So I had some contact with her. I was trying to help her with the Promethean board. Okay, so whatever. This is life. Oh, I haven't done it with this class, but we are going to look at the CDC numbers. We're going to look at the CDC numbers, and we're going to do just some simple basic calculation, nothing like what they're supposedly doing. All right, because they have access to more numbers. All right, and you just then tell me what you think about the numbers.
Mister,
Yes.
can you tell whether someone's like, I guess, like lying about some sort of, I guess, statistic, or like, I don't even know how to explain it, but like,
Okay.
like if they're like holding back certain things, like it just wouldn't make sense, like the math wouldn't check out.
Well, here's what happens. There's a lot of, historically speaking, people condemn statistics because you can make your statistics say whatever you want it to say. So they're like lies, 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 and damn statistics. Okay, that's the phrasing they use. Okay, it's when somebody quotes a statistics, it gives it an air of authenticity, which it might not be deserved. Okay, so right now, especially during the election season, there's a bunch of polls from different people, from different institutions, and when they quote it, we're supposed to take it and assume it's true. But there's so many things that go into it um, that you don't have access to. Like you have to ask them, okay, that statistic you're quoting me from where is it? From whom? Okay. All right, are those legitimate or not? Okay. So what size of the sample was? What questions did you ask? You know, who did you sample? You know, was there sufficient, did you address the bias that's gonna happen in this? How did you address it? And then you have to go through all that. And once you start finding is that a lot of them are not as good as we want. And so what we do is let's say the polls that we're looking at now. We just say, okay, we go back in the past and say how many of them were accurate 4 years ago, let's just say. And okay, so we'll look at that. But even that is dangerous, you know. But what's important is this, that whenever you hear a statistic, that you should raise an eyebrow. You don't just accept it. You think a little bit deeper and you just don't eat it up, because you got to understand, if a person is stating a statistic, okay, then you have to always decide if there's an agenda driven, if there's an agenda driven desire behind it or motivation. Okay.
So, Mr. So when they say 9 out of 10 doctors recommend it, do they mean maybe actually 10 doctors recommend it?
No, what they 9 out of 10 doctors means that let's say 90%. That's what it says. But you want to know if it's marketing, then you have to be super careful, because marketing is marketing. You know, marketing is trying to sell you something. Correct. You can always find 10 doctors who are on your side. How did you pick the doctors? You know, it's so important. How do you pick your doctors is super important. Do you randomly pick them? You know, how do we know this is true? You see what I'm saying? Like they can tell you the truth, 9 out of 10 doctors. Yeah, but they picked 100 doctors that they knew that 90 already was on their side. Who knows if the doctors are getting kickbacks? You see what I'm saying? It's very dangerous. Whenever you see anything on marketing, uh, it might not be true, but it could be true technically, that they can do it without getting in trouble with the law. You see what I'm saying? And that's how the marketing is done. You know, so all right, back to probability. But yeah, that's a great question. How about statistics in athletics? Are those biased? Are statistics in athletics biased?
No, they shouldn't be.
They
I
can't be.
doubt it.
They can't be, because either they are or they're not. You see what I'm saying? It's not based on opinion.
Yeah.
Okay. All right, let's continue. So the next thing we're going to do is called the fundamental counting principle. So we call this the fundamental counting principle. All right. So if I'll do it later. The number of ways, or the number of outcomes in a succession of events is n1 times n2 times and K. So in this case, you have two events, right? You can have two possible outcomes here and six possible outcomes there. So 2 times 6 will be 12. If you have more than two things happening, you have 3 or 4 or 5, you just keep on multiplying it through.
Mister, what does NK stand for?
So if you had 10 things, K would be 10. If you had 10 different spaces, 10 different things you did. If you had 2, then it would end here. First one times second one. If you had 3, it would be here. If you have 4, it'd be here. K says, do it until the last one, whatever K might be.
Oh wait, I thought K meant like double digits or more than one digit.
No, it could be 9. It could be 100. It just means keep on the N1. How many ways can you do the first thing? N2, how many things can you do the second thing? N3, how many ways can you do the third thing?
Mister, I'll be right back.
Yep.
Mister, what does it say? Where it says number outcomes in a, what does that word say?
A succession. And a succession.
Okay, thank you.
I should really put number of possible outcomes or total number of possible outcomes, but I'm just trying to be brief. And when you try to be brief, you end up making something less accurate, but whatever. It's an introduction to this. We'll get more accurate. But we can't get too accurate because you're not here in class, so I can force you to be more accurate. Or help you be more accurate. Okay, may I continue?
Yeah.
Okay, so let's work with the fundamental counting first. You're going to buy a car, okay? You can pick a Ford, a GM, or a Honda. Oh, I misspelled Honda, Hyundai. You can pick it in 2 sizes, compact or mid-size. And then you can do it and you can pick it 4 different colors. So you got make, size, color. It could be white, it could be red, it could be blue, it could be black. So how many ways could you pick a car? So how many
3.
how many ways can you pick the model? Sorry.
Well, make 3.
How many ways can you pick the size?
2.
2. How many ways can you pick the color?
4.
3
20.
times 2 times 4, which equals to?
20.
24.
You have 24 ways.
Oh, my bad.
24 ways. So 24 ways. So it could be a GM who's compact and who's white, or a GM who's compact and who's red. and so on and so forth. Now let me show you a different way you can do this.
I'm back.
Let me show you a different way you can do the sample space. I'll wait for some people already. Okay. I'll wait for still some people already. Guys, remember, I'm at the computer, so you have a question. I'm at the board, not at the computer. You have a question, you have to ask me. I have to hear you. Okay, so let me show you how to do the sample space for this using something called a tree diagram. So here we have a point of origin. You can have GM. You can have a Ford. Sorry, let me do it in the same order I put it. Ford, GM, or Honda. I'll just put a G for GM. If you pick the Ford, you can either have a compact or midsize. If you pick a Ford compact, you can have it in white, red, blue,
Blue and black.
or black. You see it? Or maybe white, red, blue, and black. And then you can have it here, compact, midsize. Compact, midsize. Now this gets a little bit sloppy, but let me improve it. I'll improve it. So let's say GM is here. I'll just put G. And Honda's up here. So C and M, white, red, blue, black. White, red, blue, or black. White, red, blue, or black. White, red, blue, or black. Guess what you just done? You just did your sample space using a tree diagram. Ford compact white, Ford compact red, Ford compact blue, Ford compact black, Ford midsize white, Ford midsize red, Ford midsize black, blue, Ford midsize black, GM compact white, GM compact red, GM compact blue, GM compact black. You see it? And there's 24 possible outcomes here. You can trace them all. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Now,
Mr. On the top, what letter is that? The other one, like all in top, all the way in the top.
this is just a dot. That's a big dot.
Oh, okay.
I'm assuming you'd want us to draw that.
I think you should as an example.
Okay.
You know. It's raining outside, guys.
Yeah, it's raining really hard over here.
Oh my God. No construction gets done in the rain. Like,
Yes, sir, it looks like a family tree.
It's been raining the whole week.
that's so true.
Yo, I know,
Are we
right?
turning in notes at the end of class?
I don't know. Maybe, maybe not.
That's fine. Hmm.
I might make it as the first assignment for next 9 weeks, or I might make it as the last assignment of this 9 weeks. But I think I have enough grades for this 9 weeks, so I might just make it for next 9 weeks. So you might be
Wait,
able.
Mr.
Yeah.
Mr. What's out of like the tip top one? On top of like F, G, and H.
That's just a big ass dot.
Oh, it's just dot.
Now, guys, look. If I were to ask you for your notes right now, it should take you less than 5 minutes to post it, right? There's no reason, unless you have a technology issue, that you can't post it, right? Because in theory, you should be following along with me in class, as if you were here. Now, I do understand some of you, even if you're in class, some of you might just fall asleep in class and not write anything because, I don't know, I guess you're an ultra success and you don't need to be here. But, you know, um, that's the thing. I'm noticing some of you, when I ask you to post something, and I look at the time I started asking you to post it versus the time that you post it, it could be 30 minutes. And what does that tell me? That tells me that while I was doing it, you weren't doing anything. Now, some of you are different. Some of you have already expressed to me that you do it after, or you go to the recording because you want to pay attention. That's a different story altogether. All right, maybe that's true, and I get it. I understand, but that's a skill that you're gonna have to work on, because in college, professors don't like recording anything. They're very finicky about recording anything. And in theory, our contract as teachers says no cameras in class. So right now, technically speaking, all of us are violating our contracts. I don't think an adjustment has been made in our contract. Maybe I'm wrong.
Mister.
Yes.
I wasn't here for a bit, so I just need to go back into the recording so I can check some of the notes.
That's fine. Okay. So now let's try to use the fundamental counting principle to determine how many possible codes we have. All right. I'll show you what I mean. I don't know. Some of you have cars that have like little buttons on the door to open it. Those are older cars, but cars in the mid 2000s had like buttons on it. If you don't have the key, you just press the code. So let's say you have 4 buttons here, and you can pick numbers 0 through 9. How many possible results can you have there? Well, think about it. How many numbers can you put in here? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. How many results? 10 ways. How many can you put here? 10,000 different possible results. Either you could have 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 2, all the way to 9999. Does that make sense? And one of them is the only answer to open that door. So we would say that the probability of
1 in 10,000.
guessing correct is 1 out of 10,000. That's how probability works, and that's the rule for probability. So the classical probability, or theoretical probability put probability. Probability. Its probability of an event equals the number of outcomes in event E divided by the total of the sample space.
Mister.
Yep.
Oh wait, never mind. This is guessing. Oh, never mind. I got it.
I should put guessing right.
Mister.
One second, one second.
All good.
Very stupid for that. Correct. How was the line fit today? The residual plot? So it's not here in the different section. So I'll introduce that to you in a second. If I have to look at that, that's the most important part. So don't worry about that. So, but when you check normality, you're going to be plotting that, and it comes up linearly, then you have normality. That's one way you can check for normality. Yeah, so don't worry, we'll do that.
So the correlation coefficient is like close to 1 and -1. I can just say, like, oh, it seems to be.
Yes, when you do the plot, yes. When you do the residual plot. Don't worry.
Okay, isn't that based on the correlation coefficient?
Yes, but you have to show it visually. Remember, everything in the AP stack, you have not you. In order for you to say that you can assume normality, then you show the plot, and then you show the plot looks like this. Therefore, da da da.
Okay, so then let's just like give you the numbers and just be a great match. You have to draw it out.
In many cases, you would have to, but if they do, then you can explain it, and then you explain it by looking at the plot. If they did it. Okay. Question, sir? I was helping somebody.
Mister, that word says classical, right?
Yes, classical or theoretical probability.
Okay.
Okay. So see, the probability of guessing right here would be 1 out of 10,000. What would be the probability of getting it wrong? What would it be? And this
1,000 out of 1.
over 10. Now, something interesting that happens here. Can man erase this? Yeah. This is the event that we're considering. This is what's left over. We call it the complement. Notice that the probability of the event plus the probability of whatever's left over, the complement, equals to 1. If you add these two together, you get 10,000 over 10,000, which is 1. This always happens in classical probability. In fact, it happens all the time in probability. The probability of the event plus the probability, whatever is left over or its complement, is equal to 1. All right, we're getting close to the end of class, so I'm gonna try to wrap it up. Now, another little rule that we have is you have to remember that the probability of an event is less than or equal to 1 or greater than or equal to 0. Probability of an event is less than or equal to 1 or greater than or equal to 0. So it can't be bigger than 1. It can't be less than 0. It can be 0, 1, or anything in between. And if you add up all your probabilities, it must equal to 1. When you add up all the probabilities, it must equal to 1. Type in on Google, linearity confirmed normality. Linearity to confirm normality. Read that. May I erase, guys and gals?
Give me a second. Give me a second.
No.
Yeah, just give me a second.
I'll wait, I'll wait.
Okay, yes.
Hang on, hang on.
Mister. The O is outcome? Oh, I mean 0. No, it's a 0.
That's 0, that's 0.
Never mind.
All right.
Sorry, mister. My Wi-Fi went out again.
Okay, I guess that's gonna happen with all this rain constantly.
Yeah, it's been thundering in my area too, like this whole time. It's been like this since like 2 a.m. It really sucks.
It's been raining like really hard.
Well, that means my construction projects are like, nobody works today.
Oh yeah, Mister. By the way, how's the pool?
The pool is good. The owner has to do his deck soon. And then I'll finish it. I'll finish it up within the next 2 or 3 weeks, but
Nice.
I'm not in a hurry. The other pools we're building and with the other company, Vision Pools, I don't know, because I don't really get involved in that company as much because, you know, I'm not running those projects, but we'll be fine. We'll make some money. I don't know. I hate pools. All right, Mary Race? Yeah. All right.
Yeah.
So let's do a poll. Let's do an imaginary poll in this class. This is imaginary. So elections are about to happen. We have Trump on the ticket. We have Biden on the ticket. We have Kanye on the ticket. I think Mary Poppins is on the ticket too. All right. We have 42 students in the class. All right. So let's say 15 students are going to vote for Trump. Let's just give Biden the advantage. 16 students are going to vote for Biden. 3 students are going to vote for Kanye. And what's the remainder? That's 16 plus 15 is 31. 6.
Mister, make Kanye 4. How made it?
So not bad. So some of the frequency here is 40. We have 40 kids. So now I ask you, now we're going to have more kids come in. What's the probability the next kid, the 41st kid, will vote for Mary Poppins?
It's 1 in 4.
Yeah, Mary Poppins for president, boys.
Oh, you want to? Okay, I got you.
This is called empirical probability. 15%. This is called empirical probability. Empirical probability is probability of an event equals the number of outcomes in that event or the frequency of the event. So the frequency of the event you're considering, the frequency of the event divided by the total number of the event. Total number of events. Or you can just say total frequency, which is this. That's called empirical probability. It's not classical. Classical probability is when each of the outcomes was equally likely. Is it equally likely to choose Trump, Biden, Kanye, and Mary Poppins? No. But it was equally likely to pick any one of these numbers. You see? That's what makes it classical probability versus empirical probability. Okay, so I'm gonna send you the one I have in my notes. I'll point out where it is. It's actually very easy on the PowerPoint. Yeah. I'm gonna send you the PowerPoint or tell you where it is on yours. If I stop reviewing it, I'll do it again. Okay, no problem. So this leads us to finalizing this section. And it's called the law of large numbers. Okay? Essentially what the law of large numbers says is if you repeat an empirical experiment over and over, you do it over and over, the probabilities approach the theoretical probability or true probability, whatever they might be. You can change this to actual. So as you repeat an empirical experiment for a very long time, the numbers, so if you kept on doing this poll here, and it got big enough, and you did it properly, you can tell who's going to become president. And so that's why these polls are interesting in the upcoming weeks. I don't know if I'm going to be able to explore it as well with you guys because we have dual modality and it's so much easier when everybody's in class. But it'd be interesting what's going to happen in 14 days. You know, maybe we don't know the results so after, but it'd be interesting to know and to compare. You know, to see which polls were most accurate, and then to theorize or to talk about maybe why they went wrong. Or if they went right, or they were completely right, and maybe they were right. I know in 2016 they were super wrong. Super wrong. All right, guys, so I think that's a wrap. You have.
Wait, I still gotta write that.
You have. Well, you guys don't have to worry, so don't post it. I know. You have 7 minutes, 8 minutes to post your stuff on post for Teams. I'm gonna be looking at the time.
Mister, I need to write now. Thank you.
All right, so make sure you guys post the stuff up there. Class is over 8:56. If you're done writing notes, post it up. You can peace out. I'll go ahead and stop the video.
Hang on, I just gotta export the file.
Okay.